A Harvard astrophysicist just published a paper showing that interstellar object 3I Atlas is loaded with enough deuterium fusion fuel to produce a 10-teraton nuclear explosion, roughly 200,000 times the largest weapon ever detonated on Earth. James Webb's and ALMA confirmed the deuterium concentration, and Avi Loeb did the math on what happens if a fission trigger sets it off. The answer rewrites the planetary defense playbook. Over the next 20 minutes, you're going to find out exactly what the data shows, why every nuclear deflection plan written since 1994 has just been disqualified, and what the next interstellar visitor is going to force humanity to decide. Let's get into it. On April 24th, 2026, Harvard astrophysicist Avi Loeb published a paper that quietly reshapes how planetary defense has to be done. The title is direct. Can an atomic explosion ignite a chain? Reaction of deuterium in 3I Atlas. The answer the paper arrives at is yes, and the consequences are catastrophic. Loeb's calculation concludes that if a fission bomb trigger were placed inside the interstellar object, 3I Atlas, it would ignite a self-sustaining deuterium fusion chain reaction. The total energy released would be approximately 10 teratons of TNT. That is roughly 200,000 times the yield of the largest nuclear weapon ever detonated by any nation on Earth, the Soviet Tsar Bomba, and approximately 5 to 10% of the energy released by the Chicxulub impactor that ended the age of dinosaurs. But where Chicxulub delivered its energy over many seconds of kinetic deceleration, Loeb's 3I Atlas detonation arrives in approximately 1/100th of a second. Pure nuclear release. This paper is not a warning that 3I Atlas is going to hit Earth. It is not. The object is the third confirmed interstellar visitor to enter our solar system. It has already transited the inner solar system on a hyperbolic trajectory, and it is now over 1 billion kilometers from Earth and accelerating outward. By the end of the year, it will be beyond practical observational reach. The paper is something else. It is a warning about the next object like it, because 3I Atlas is no longer a singular event. It is the third interstellar visitor humanity has detected, after 1I Oumuamua in 2017 and 2I Borisov in 2019, and the data 3I Atlas has just delivered, says that something we assumed was true about every previous proposal for nuclear planetary defense may not be true at all. Here is what the data says, here is why it matters, and here is what the next interstellar visitor is going to force us to decide. The paper Loeb published in April is built on two earlier observational results from March of this year. Both use the most powerful telescopes humanity currently has pointed at small bodies, the James Webb Space Telescope and the Atacama Large Millimeter and Submillimeter Array, more commonly known as ALMA. The James Webb measurement, posted as a preprint in early March 2026, used infrared spectroscopy to study water vapor outgassing from 3I Atlas as the object passed through the inner solar system. The measurement targeted the ratio of deuterium to ordinary hydrogen in the water, the standard isotopic fingerprint that astrochemists use to tell where a small body originated. The result was a deuterium to hydrogen ratio of approximately 0.95%. That works out to roughly 1 deuterium atom for every 100 hydrogen atoms in the water vapor. The ALMA measurement, posted as a preprint on March 20th, 2026, used millimeter wave spectroscopy to study methane outgassing from the same object. The result was a deuterium to hydrogen ratio of 3.31%, plus or minus 0.34%. That works out to roughly 1 deuterium atom for every 30 hydrogen atoms in methane. Now those numbers don't mean anything until you put them next to a reference scale, so here is the reference scale. The cosmic average deuterium to hydrogen ratio, the baseline that was set during Big Bang nucleosynthesis in the first few minutes after the Big Bang, is approximately 1 deuterium per 40,000 hydrogen. That is the floor against which everything else gets measured. Earth's oceans, the standard reference for cometary water comparisons, sit at approximately 1 deuterium per 6,500 hydrogen, a few times higher than primordial. Solar system comets typically measure deuterium to hydrogen ratios in water at approximately 1 part in 2,000 to 1 part in 10,000. The European Space Agency's Rosetta mission to Comet 67P Churyumov-Gerasimenko measured methane deuterium ratios approximately 14 times lower than what 3I Atlas just delivered. So 3I Atlas is not a slight outlier. The methane number, 3.31%, is roughly 1,000 times the cosmic average. It is the highest deuterium concentration ever measured in any small body, in any context, anywhere. And it is not a single instrument result. Two completely independent telescopes, James Webb in infrared, ALMA in millimeter, using completely independent observational techniques on completely independent molecular tracers, water and methane, both find that 3I Atlas is dramatically deuterium enriched. Whatever this object is made of, the deuterium signal is real, and it is extreme. That is the data Loeb's paper is built on. Now, here's why deuterium, specifically, is the part of this story that should make you pay attention. Deuterium is a hydrogen atom with an extra neutron in its nucleus. It is stable, naturally occurring, and not radioactive. Water made with deuterium instead of ordinary hydrogen is called heavy water. In a glass of tap water, roughly 1 in every 6,500 water molecules contains a deuterium atom. That is just how the universe is built. So far, none of this is dangerous. What makes deuterium different from ordinary hydrogen is what happens when you push two of them together hard enough. Deuterium fuses. It is, in fact, the preferred fuel for every serious fusion energy program on Earth, including the National Ignition Facility's inertial confinement experiments and the International ITER project's magnetic confinement reactor. Fusion engineers prefer deuterium for 3 reasons. First, it ignites at a lower temperature than other candidate fusion fuels. Second, when it fuses, it releases substantial energy per reaction. Third, it is stable enough to handle and store without exotic infrastructure. If you are designing a fusion reactor, deuterium is the first thing on your shopping list. If you are designing an interstellar fusion drive, deuterium is the first thing on your shopping list. If you are designing a hydrogen bomb, deuterium is the first thing on your shopping list. So when James Webb and ALMA reported that 3I Atlas contains 1% deuterium in its water and 3.31% deuterium in its methane, what they were reporting in functional terms is that the object is loaded with fusion-grade fuel. A fusion engineer looking at the isotope ratios of 3, I Atlas could not, on the data alone, distinguish this object from a deliberately enriched fuel reservoir. That is not a metaphor. That is the literal physical reading of the numbers. And it is the reading that prompted Avi Loeb to ask the question almost no one else in astronomy has been willing to ask. What happens if you set it off? Loeb's April paper walks step by step through what the physics actually does, if you assume a fission bomb trigger detonating inside 3I Atlas. The chain begins with that trigger. A standard fission device, the kind of nuclear weapon that has been in human arsenals since 1945, detonates at the core of the object. Temperatures at the trigger reach tens of millions of degrees Kelvin. Pressures crush atomic nuclei together, overcoming the electrostatic repulsion that normally keeps them apart. That is the spark. What happens next is the part that requires the deuterium concentration to be as extreme as 3I Atlas just demonstrated. 2 deuterium nuclei collide. There are 2 possible outcomes with roughly equal probability. In one branch, the nuclei fuse to produce tritium plus a proton, releasing 4.03 million electron volts of energy. In the other branch, the nuclei fuse to produce helium-3 plus a neutron, releasing 3.27 million electron volts. Either way, energy is released, particles are released, and the local temperature rises. So far, this is just textbook deuterium-deuterium fusion. But then the secondary reactions begin. The freshly produced tritium fuses with surrounding deuterium in a reaction that releases 17.6 million electron volts, roughly 4 times the energy of the original fusion event, and produces an additional neutron. The helium-3 from the other branch fuses with deuterium to produce helium-4 plus a proton, releasing 18.35 million electron volts. Each new fusion event releases more energy, more neutrons, and raises the local temperature still higher. Those neutrons are the engine of the chain. Each one finds another deuterium nucleus, ignites another reaction, releases another neutron, and the wave propagates outward through the body of 3I Atlas. A detonation front forms. It moves through the deuterium-loaded material at velocities limited only by the sound speed in the medium, and the deuterium-loaded material is everywhere, in the water, in the methane, and whatever else the object is made of. Loeb's calculation puts the propagation timescale at approximately 1/100th of a second. That is the sound crossing time across the body of 3I Atlas, from the moment the fission trigger fires to the moment the entire object disintegrates in a fusion fireball. 1/100th of a second. That is not a slow burn. That is the chain reaction running to completion before any cooling mechanism can possibly intervene. Loeb's energy budget calculation uses 3 numbers. The first is the minimum mass of 3I Atlas, 1.6 times 10 to the 11th kilograms, or 160 million metric tons. That figure comes from a separate paper Loeb co-authored with researchers Valentin Thos and Andy Burkert, derived from outgassing observations and orbital dynamics. The second is the deuterium content, scaled by the deuterium to hydrogen ratios James Webb and ALMA actually measured. The third is the energy released per deuterium fusion reaction. When you multiply those three numbers together, you get approximately 4 times 10 to the 22nd joules of total energy released, if the entire deuterium content fuses. In TNT equivalent units, that is approximately 10 teratons. Now, 10 teratons is a number that needs context to be meaningful, so here is the context. The largest nuclear weapon ever detonated on Earth was the Soviet Tsar Bomba, tested over Novaya Zemlya on October 30th, 1961. Its yield was approximately 50 megatons. A 10 teraton release equals approximately 200,000 Tsar Bombas. Stack 200,000 of the most powerful nuclear weapon humanity has ever built into a single instantaneous detonation, and you arrive at the energy budget of 3 I-Atlas going off, or compare it to a different reference point. The Chicxulub impactor that ended the Cretaceous period, approximately 66 million years ago, released somewhere between 100 and 300 teratons of TNT. A 10 teraton 3I Atlas class detonation is roughly 5 to 10% of that, but it arrives in 1/100th of a second instead of over the duration of an impact event. What does that look like as a physical effect on Earth? Standard nuclear weapons effects scaling laws use a cube-root relationship between yield and damage radius. For a 10 teraton near-Earth space detonation, the radius for severe structural damage, the kind of overpressure that flattens reinforced buildings, would extend on the order of 1,000 kilometers or more. That is enough to engulf entire countries in a single blast wave. Multiple smaller U.S. states would simply cease to exist in any infrastructural sense. Continental-scale thermal pulse would deliver third-degree burns and ignite fires across thousands of kilometers on multiple continents simultaneously. And then comes the fallout. A fusion-dominated burst with neutron-activated debris produces fallout that is hemispheric to global in scale, depending on burst altitude and atmospheric circulation. Multi-year contamination of soil, water, and food chains. A forced nuclear winter on top of a directly inflicted thermal pulse on top of a continental blast wave. This is the package that is sitting inside 3 I-Atlas, waiting for the wrong kind of human intervention to ignite it. There is a standard physicist rebuttal to claims of this kind. It goes back to 1942, during the Manhattan Project, when Edward Teller raised the possibility that the fireball from an atomic bomb explosion might ignite atmospheric nitrogen into a self-sustaining fusion reaction. Hans Bethe responded with calculations demonstrating that radiative losses would prevent atmospheric ignition. Energy bleeds away from the surface of any heated region faster than the chain reaction can deposit it. The fire goes out before it can spread. That argument was formalized in a 1946 declassified report by Konopinski, Marvin Jr., and Teller. The report concluded, and I am quoting directly, whatever the temperature to which a section of the atmosphere may be heated, no self-propagating chain of nuclear reactions is likely to be started. That conclusion has held for nearly 8 decades. It is the reason every nuclear weapon ever detonated has produced a contained mushroom cloud rather than a runaway atmospheric ignition. Loeb's paper accepts this conclusion for the atmosphere and then identifies why the same argument fails for 3 I-Atlas. The Bethe argument works for the atmosphere because the atmosphere is thin and transparent. Radiation from a hot column of air can escape sideways and upward into space, carrying energy away faster than fusion can deposit it. Surface area is high relative to volume. Cooling wins. For 3 I-Atlas, the geometry is reversed. The object is opaque, solid density, and roughly kilometer scale. Radiation from the interior cannot escape through anything except the surface. The interior fuel reservoir is shielded by overlying material. Volume is high relative to surface area. For radiative losses to compete with the volumetric energy release in the interior, the surface of 3 I-Atlas would have to reach temperatures of millions of degrees Kelvin. By the time the surface gets that hot, the interior temperature has long since exceeded the deuterium ignition threshold, and the detonation wave is self-sustaining all the way out to the surface. This is the same physical reason a tamped fission-fusion weapon, a hydrogen bomb, works in the first place. The tamper holds the fuel together long enough for the chain to complete before surface losses can drain it. 3 I-Atlas, by virtue of being a kilometer of opaque rock and ice, is its own tamper. Loeb's paper is, in effect, an update to Hans Bethe's 7-decade-old calculation. Applied to a geometry Bethe was never asked about. The conclusion is the opposite. For an opaque, solid-density object loaded with fusion-grade fuel, the chain reaction does not go out. It goes all the way through. The physics Loeb is using in 2026 is not new. It comes from a paper by Konopinski and Teller published in 1948. in Physical Review, Volume 73, page 822. That paper provided the first theoretical calculation of the fusion probability of two deuterium nuclei colliding under bomb fireball conditions. That calculation became one of the foundational references for the development of the hydrogen bomb. The two-stage thermonuclear weapon design, which both the United States and the Soviet Union pursued and tested through the 1950s and 60s, used a fission primary stage to generate the high temperature and density conditions that the Konopinski-Teller calculation showed would ignite deuterium fusion in a secondary stage. Every multi-megaton thermonuclear weapon in every nuclear arsenal on Earth is, at its physical core, an application of that 1948 paper. The architecture is well understood. A fission bomb fires. The radiation pulse compresses and heats a deuterium-loaded secondary stage. The deuterium ignites. The chain reaction completes before the bomb has a chance to fly apart. Energy is released in megaton quantities. In a hydrogen bomb, the deuterium is loaded into the secondary stage by human engineers who know exactly how much they are putting in and where they are putting it. In 3I Atlas, the deuterium is loaded into the body of the object by something. By whatever process produced the deuterium concentration there. We don't yet know what that process is. The natural fractionation pathways that astrochemists invoke to explain modest deuterium enrichment in interstellar ices have trouble producing the magnitude that James Webb and ALMA actually measured. Loeb has a candidate alternative explanation, and it is not a comfortable one. But the physics of what happens if you ignite the body, that part is settled. It is the same 1948 calculation, only the geometry has changed. In July 1994, the fragments of comet Shoemaker-Levy 9 impacted Jupiter. It was the first directly observed major comet impact on a planet in human history. The impact scars on Jupiter's atmosphere were visible from Earth for weeks. Photographs of the impact sequence ran on the front pages of newspapers worldwide. Edward Teller, by then in his late 80s, responded with a proposal. Humanity, he argued, needed a planetary defense capability scaled to handle a similar event aimed at Earth. He sketched out a design for a nuclear explosive device with a yield of approximately 1 gigaton of TNT, scaled to match the kinetic energy of a kilometer-class asteroid impactor. That proposal, documented in Lawrence Livermore National Laboratory technical reports and later reviewed in policy literature on nuclear planetary defense, became the foundation of the modern nuclear deflection playbook. The basic concept comes in two flavors. A nuclear standoff burst, detonating a weapon at a calculated distance from a hazardous object, delivers a thermal pulse that vaporizes a thin layer of the object's surface. The recoil from the vaporized material acts as a kinetic deflection force. Aimed correctly, with sufficient warning time, this can nudge an inbound asteroid off an Earth-crossing trajectory. The second flavor is the subsurface burst. The weapon is delivered to a position inside the body, by penetrator, by docking, or by other means, and detonated within the material. This delivers significantly more momentum, but at the cost of fragmenting the body into multiple pieces. NASA, the Department of Energy, and Lawrence Livermore National Laboratory have continued to study and refine these options for 30 years. They remain the contingency plan for any inbound object that is detected with insufficient warning time for slower deflection methods like kinetic impactors or gravity tractors. Loeb's 2026 paper is the first to identify a class of inbound objects for which the subsurface burst, flavor 2 of Teller's proposal, is operationally disqualified. For an object with 3 I-Atlas's deuterium concentration, the subsurface burst does not deflect. It detonates. The trigger meant to break the threat into manageable fragments instead ignites the body into 10 teratons of pure nuclear release. Every nuclear deflection proposal made since the 1948 Konopinski-Teller paper has assumed, implicitly, that the target body is not itself loaded with fusion-grade fuel. Loeb has just identified the first target population where that assumption fails. And as of today, that population contains 3 I-Atlas. And we don't know how many other objects like it are out there. Loeb's April paper raises the planetary defense question. But his March 2026 companion piece, which is what really set the deuterium discussion in motion, raised a different one. Loeb asked it directly. Since deuterium is fusion fuel, could its overabundance in 3 I-Atlas flag a technological signature? The honest scientific position on that question is precise, not proven, not ruled out. The natural pathway for extreme deuterium enrichment in a small body, ion molecule fractionation chemistry in cold protoplanetary disks, requires temperatures below approximately 30 Kelvin. Those temperatures exist in present-day molecular cloud cores. The problem is that 3 I-Atlas, on the strength of its trajectory and its isotopic signatures, looks ancient. If the object formed 10 to 12 billion years ago in a primordial star-forming region, the cosmic microwave background at that epoch was already at 30 Kelvin or warmer. A protoplanetary disk immersed in that radiation field cannot itself fall below the ambient temperature. The cold disk fractionation pathway therefore requires either a younger formation epoch, which doesn't fit the trajectory data, or a fine-tuned shielded high-density region inside an older disk, which is theoretically possible but doesn't comfortably reproduce the magnitude of the observed enrichment. Combined with 3I Atlas's other anomalies, the non-gravitational trajectory perturbation that doesn't match standard outgassing models, the trailing structure interpreted by some observers as a debris stream, the conjunction of unusual properties starts to look unlikely as a series of natural coincidences. There are framings circulating online that go further. The claim that 3I Atlas is confirmed alien technology overstates what the data actually supports. It is the strongest single technosignature candidate from a small body observation, but it is not proof. The claim that mainstream institutions are suppressing the technosignature interpretation does not fit how the information has actually flowed. The James Webb and ALMA data are public, Loeb's calculations are public, and the conservative interpretation is the institutional default. The speculative interpretation is the one being pushed by a tenured Harvard professor whose career has not been damaged by it. If anyone is being suppressed, it isn't Loeb. The defensible position is the one Loeb himself takes. The deuterium concentration in 3I Atlas is the strongest single technosignature candidate from any small body observation in modern astronomy. It is not proof. It is the kind of data point that should drive aggressive observational follow-up of every future interstellar visitor that arrives within reach of our telescopes. And whether 3I Atlas turns out to be a natural freak of astrochemistry or an artifact of an advanced civilization, the planetary defense calculation is the same. A fission trigger inside it produces 10 teratons. It does not care which one of those answers is correct. 3I Atlas itself is no longer a planetary defense concern. It is over 1 billion kilometers from Earth on an outbound trajectory and accelerating away. By the end of the year, it will be beyond the practical reach of even our largest telescopes. The window for close-range study is closed. What is not closed is the operational implication of what just got measured. 3I Atlas is the third confirmed interstellar object humanity has detected. The empirical fraction of interstellar visitors that show extreme deuterium enrichment is now 1 out of 3, 33%. That is not a meaningful statistic at sample size 3, but it is a non-zero number, and it tells us that the next interstellar visitor that arrives in our neighborhood may carry similar anomalies, or different ones, or none. We won't know until we measure. Detection to impact timescale for an interstellar body on an Earth-crossing trajectory can be weeks. 3. I Atlas itself was detected only weeks before its inner solar system passage. That is shorter than the lead time we currently need to perform spectroscopic characterization of an inbound object. Both James Webb and ALMA are heavily oversubscribed, and getting urgent observation time for an unscheduled target requires institutional gymnastics that take days at minimum. NASA's NEO Surveyor mission, a Lagrange point infrared telescope designed specifically to find inbound near-Earth objects earlier than the current ground-based survey network can, has a planned launch date no earlier than September 2027. NEO Surveyor will substantially improve early detection capability for incoming small bodies, including interstellar visitors. It will not, by itself, solve the spectroscopic characterization gap. That problem requires additional infrastructure that does not currently exist. Here is what to watch for in the weeks and months ahead. Any new interstellar object detection announcement, any follow-up spectroscopy of 3I Atlas as it recedes, there may still be measurable signal during the next year. Any update from NASA, ESA, or the National Academies on planetary defense protocols incorporating composition-dependent deflection options. Any peer-reviewed response to Loeb's chain reaction paper, particularly from the astrophysics and nuclear physics communities. Avi Loeb's paper has not changed the immediate threat picture. Earth is not in danger from 3I Atlas. Earth has never been in danger from 3I Atlas. What has changed is the long-term planetary defense calculation. The deflection playbook humanity has been refining since 1994 assumed the target body would not itself be a bomb. Loeb just identified the first target population where that assumption fails. The next interstellar object that arrives is going to force a decision, and the decision is going to have to be made faster than the current detection and characterization infrastructure can comfortably support. We will be tracking this as it develops.